Hi, my name is Christina and today I'll be talking about my constant velocity motion lab. So the purpose of the lab is to observe the motion of some object moving at the same speed without changing direction and comparing the observed and predicted motions. The observed motion will be demonstrated with the tracking of a real-life video of a tennis ball, and the predicted motion will be demonstrated with a hypothetical computational model in GlowScript. So some fundamental principles are the momentum principle and Newton's first law. We will apply these concepts to the lab further into the video. So some potential errors in this experiment, the only force acting upon the object should be my push in the beginning. But in real life, there are all kinds of invisible and unnoticeable forces that may have affected the object's motion, such as friction, gravity, etc. It will be difficult to account for these forces using a theoretical formula. So here's the graph. As you can see, the experiment and computational model displays different results. Let's see why. So Newton's first law, which is one of the fundamental principles we'll be talking about, an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. We are trying to demonstrate this by showing that the object continues moving the same way from start to end in this experiment. We would first have to know what the velocity is to conduct these tests. That's where the momentum principle comes in which we derive the formula to understand that the initial velocity is the same as the final. This means that the velocity is constant, and we can use our calculated velocity for both the experiment and the computational model. So some tools that we used is GlowScript, which develops our computational model, and a tracker, which collects data on the motion of a real-life video. So as you can see on the picture, the system is the ball and the surroundings is multiple things, such as like the air conditioning, me, the not smooth floor. So here are the initial conditions, and like I said before, because Fnet is 0, then Fnet is constant, so we can calculate the velocity with the following formula, and when we plug in the values we obtained from the experiment, we get an average velocity of negative 0.672. Now, here is the steps I used to do my experiment. I filmed a tennis ball rolling across the floor, making sure the lighting and the camera quality are acceptable. Then I cut the clip accordingly and used the tracker to obtain data points on its change in position, tracking each frame. For the computational model, in order to predict the future and the ball's motion, we replace lines of code for the position and velocity update equations. I used the tutorials to adjust my code accordingly so that it would demonstrate the ball's motion in a zero net force environment. Unlike the experiment, the computational model is perfect for running situations in which Newton's laws hold true. The distance change is consistent and the velocity is constant as shown in the graph. So some similarities between the two lines is that the graphs are super close to one another, almost identical except for a slight gap. They both have a downward slope, so in both cases, the velocity is negative with similar magnitudes. But there's many differences. The line for the computational model is constant and linear, whereas there's a slight curve in the line for the experiment. The experiment must have accounted for friction and other forces which probably affected the ball's motion and thus affected my tracking, in which the ball must have slowed down and covered less displacement as time went on. This is made noticeable in the gap between the two lines. Since the line is curved, this means the velocity was not constant in the experiment. Theoretically, the velocity should be the same for both the experiment and computational model, since the velocity should be constant and consistent, but that is impossible. Possible sources of error may have been related to the inaccuracy and preciseness of measurements on the tracker. The frames weren't blurry, but even so, it's difficult to pinpoint the point mass with just the human eye. Another source of error could be related to the surroundings and its forces. So for the what if and what does it mean questions, if we flip the axis, the direction of the slope would change and thus the velocity would change too. Velocity is the combination of both the direction and magnitude, so the velocity will stay the same in terms of magnitude, but the experiment and computational model would show the object moving with an upward slope on a position time graph in which the velocity would be positive. What does it mean? No, it is not possible for me to say how many pushes and pulls are added together to give zero net force. With the large variety of forces to account for, it's difficult to know the magnitude of each different force and what forces should be accounted for in this situation, like the moon's gravitational force on the object, for example. Now, conclusion. We discussed the purpose of the lab as well as the results found in the experiment and computational model and how physics applies to these situations.